Swayam Prabha. Digital India. Educated India.
This is lecture number 8. Hello everyone, welcome back. Today we are going to start a very important topic, that is the governing equations. So, as we have discussed that computational fluid dynamics is an approach to computationally simulate the governing partial differential equations that govern the fluid flow. Okay. So, that is what we are going to do now. So, we are going to derive the governing equations, although we will not be going in too much of detail, because this is not a fluid dynamics course and it is expected that you may be knowing these equations already, but because these are very important or very central to this course, we will be discussing the aspects which are important for CFD. So, as you know, there are three conservation law, primarily three conservation law. Okay. There is mass conservation, okay, which is basically mass in, if you make a body like this. Okay. So, this is mass in, mass out is equal to rate of change of mass. Okay. Mass. Okay. So, if there is no rate of change of mass, basically if you are not adding any mass or if you are not taking out any mass, then the m dot in will be equal to m dot out. So, mass flow rate in will be equal to mass flow rate out. Okay. Similarly, you can have the momentum conservation. Okay. So, the momentum conservation is now this mv, okay, in, mv out. Okay. And then you might have some forces acting on that fluid element. So, what you are showing here is the kind of control volume, and we will come to the discussion of what is the control volume. But borrowing the idea that we have for derivation of any conservation equation. So, if this is a boundary, okay, and this is the volume, okay. So, from the boundaries the fluxes can get in and then get out, and then you can have some source term, some forces which are acting on the body, and you have to basically balance all these forces to make sure that whatever the change is happening in any quantity, whether it is mass or momentum or energy, is taken care by the forces supplied. Okay. So, we will have the momentum in, momentum out, and that should be balanced by the rate of change of momentum and the forces acting on the body. Okay. Basically, that is the Newton's second law of motion. Okay. This is Newton's second law. Okay. And finally, you have this energy conservation, that means that following the first law of thermodynamics, okay, which you have already discussed. That if you are adding any heat, that will be used to get work done plus increase the internal energy. Of course, this energy conservation is important only when there is a change in temperature, and which is basically the case of the compressible flow. Okay. Because compressible flow deals with the change in density. Okay. So, if the density is changing, then that means by your ideal gas equation, or even in real gases or anywhere where there is a relation between pressure and density and temperature, your temperature will change. Okay. So, wherever the temperature change is involved, this will lead to you need to have an energy conservation equation also. Now, this energy conservation can be of many different form. I will see those in lectures. Okay. It can be the just the internal energy, or maybe the internal plus kinetic energy, internal plus kinetic plus potential energy, plus you can have the thermal energy equation, total energy equation, kinetic energy equation, and so on and so forth. Okay. So, let us go by one. Okay. So, the first basic principle you might have read is the Reynolds transport theorem. Okay. So, why Reynolds transport theorem is needed is because I talked about the Newton's second law, okay, and then the first of thermodynamics. All these equations or all these laws were derived for a control system. Okay. What do you mean by control system? So, the control system is it is basically a collection of particles, okay, and through which the matter can go out. Okay. So, let us say if you have a particle, okay, and if you are observing how it is moving in the flow, okay, and what are the forces acting on that particle. So, you can use this control system approach. Okay. But the problem with this control system approach or the system approach is that there are too many particles, okay, in the fluid, okay, and tracking each particle and trying to balance the forces on every single particle becomes very tedious. Okay. So, this approach of tracking individual particle and seeing how the forces are balanced on that, this approach is called the Lagrangian approach. Okay. So, the system is basically a representation of the Lagrangian approach. What we rather prefer in control volume or in fluid flows is that instead of tracking individual particle, we can set up our camera at one place, let us say here, okay, and we will see that how the particle movements are taking place. They might be getting in, going out, okay, and within this control volume you can apply all our laws. Okay. So, this gives you a handle that you do not need to basically track individual particle. Okay. So, this approach is called the Eulerian approach, and this is more popular in fluid flows just because it is simple to basically fix an area and see how the fluid motion is taking place there rather than basically individually tracking a particle. But then we need to basically translate all the laws that we have for the Lagrangian into this Eulerian framework. Okay. So, the system is basically will have the fixed mass, okay, and control volume will not have a fixed mass, but rather we will have a volume. Okay. So, what Reynolds transport theorem does is basically it connects the system to the control volume. Okay. So, basically if you have any change in derivative into the control system, okay, or the control mass system, and if you have any derivative change in the control volume, we can relate both these derivatives for any extensive properties. So, extensive properties are something which are basically dependent on mass. Okay. It can be mass itself, or you can have momentum, you can have angular momentum, linear momentum, okay, you can have energy. Okay. So, it is if I can write it m, this is mv and this is I can call it E. Okay. And then there will be corresponding intensive property to that will be per unit mass. So, for this it will be 1, for this it will be velocity, okay, for this it will be energy per unit mass, right. So, these are the extensive properties. And these are the intensive properties. Okay. So, let us take an example of the system and control volume. So, what I am showing here in this particular case, the diagram here is the position of a system and the control volume. Okay. Let us say at time t, the system as control volume are basically nearly overlapping to each other. Okay. Now, your control volume is fixed, okay, as time passes, okay, the system will move because we have discussed the system is a collection of particle. So, with any force or any action the system will move, right. So, let us say this the red dotted line here is the system which moves here to the point t plus delta t, okay, with time because of some force or whatever action is happening. Okay. But the control volume remains fixed. The control volume, this is fixed, which is our observation, and this is moving, okay, due to some action. Right. Now, we want to basically relate. So, we know the relations for this framework, okay, but we do not know the relation for the framework which is the control volume. So, if you go by the derivations of the Reynolds transport theorem, Okay, we can say that so you can basically what you could do is like if you have let us say this is your control volume and let us say this is your system, okay, and you can find an overlapping region, this is 1, 2 and 3, okay, and then take any extensive property which is let us say B, okay, and find out the rate of change of this property system, okay, and then you will see that there are the B at initial condition T is defined by this 1 and 2, and then at T plus delta T it is defined by 2 and 3, right. So, if you want to find that out, okay, and what is your control volume in this is basically this region, okay. Okay, ultimately we will make an approximation that the movement in the system is so small, because we are talking about dt, is that this the boundary and of the control volume as well as the system are nearly overlapping, okay. So, if you do this, you will find one expression, okay, which will be only for 2, okay, which is basically B t plus delta t minus B t, okay. This is for by delta t limit delta t tends to 0, and this will be for only 2 region, okay, but then you have also changes in 3, okay, and changes in 1, okay. So, this is your system, and this what this can be defined, this is for the control volume. So, this can be written as delta B by delta T. So, remember this is dB by dt, because now the system is moving. So, whatever changes that is happening due to the movement is captured here, okay, by d by dt, there is no other partial derivative, but when it comes to the control volume, you will have delta B by delta T, which is basically the rate of change of the quantity B, okay, and plus you will have changes 3 and 2. So, basically that is the net flux, and that will be through the surface. So, you can call it control surface, right. So, these boundaries are basically the control surfaces, right. So, whatever you see, these are the control surfaces. So, the blue boundary is your control surface, okay. The change in the system is equal to the rate of change in the control volume plus the fluxes going through the control volume. So, going through and coming in, right. So, at any given time you will have fluxes coming in from 1 and going out from 3, right. So, the same thing is written here in the next slide. You can see that your d by dt system, okay, is which is the rate of change of B in the system is equal to rate of change of B in control volume and plus net flux or net flow rate of B, okay, which is B dot net. If you want to write this in the integral form, okay, this is dB by dt equal to system, and if I can make a control volume like this, okay, and then let us say this is my elemental area dA, okay, and there is a velocity here, okay, this is u, okay, at which any quantity is going out, and then you will have this normal component, this is u dot dA, right. So, what is the rate of change of B in control volume? So, that can be written for this entire volume, okay, this is for this entire volume, is rho is basically density, B is the intensive quantity, okay, and this is the change in elemental volume, okay, dV, and which will be basically integrated over the entire volume, okay. This is your rate of change of B in the control volume, okay. Remember B is nothing but rho BV, right, rho into volume. So, that will be mass multiplied by B. So, that is why when you say dB by dt, okay, so we will have this rho B dV, okay, because we are integrating it over the surface, and the surface can be of any form, okay, this can be like this or any other form, right. So, that will be rho B dV, okay, V is the volume, and that will be for the entire control volume, okay. And then you will have flow rate. So, the fluxes, some fluxes will go in and some fluxes will go out, but if you can take the normal here. So, if this is the way the normal is defined, n is given here, right. So, you can just write this u dot n, okay, and multiply this whatever quantity that you have rho b, okay, and then dA. Okay. This is through the control surface, okay, and this can be written as u dot dA, where dA is basically area normal. So, normal is taken care here. So, rho b u dot dA, right. So, we got the expression, the change in system is equal to the change in control volume plus the net flux, right. So, we can use this Gauss divergence theorem here, okay. Yeah, you can directly use the Gauss divergence theorem here. So, this will be del by del t, okay, and this is for the rho b dV, okay, for the control volume, and this will be for the control surface, and if you use that, that will be rho double dot rho b u, okay, dV, right. This is what the Gauss divergence theorem is. It changes from area to the volume, right. And if you use this entire thing, that will become del by del t, okay. Sorry, if you now make an assumption that your control system is stationary, then del by del t can go inside, okay, and then you can take this integral sign out, okay. Sorry, this will not be the surface, but this will be also the volume integral, okay, when you convert it to the volume, okay. So, this is surface and this is volume. So, then it will become, this expression will be del by del t rho b plus del dot del dot rho b u, okay, dV, okay. So, this is your relation, this is for the control volume and this is for the system. Now, what you can do for, you can take different quantities for mass, momentum and energy and get those different conservation equations. For example, if you take B equal to 1, okay, that is what that will be. So, that if B equal to 1, then B is just mass, right, that is the mass conservation. If we take B equal to V, any velocity, okay, you may take x velocity, y velocity, z velocity, okay, and then B equal to mv, okay, that is the momentum. So, you can get the momentum conservation, and similarly if you take B is the energy per unit mass, okay, it can be internal energy or kinetic energy, okay, and then you can get the energy conservation equation. So, I will just show you one expression for the mass conservation, okay. So, that will give you the integral form of the equation, and then similarly you can derive for the momentum conservation, okay. So, for the mass conservation, the B is equal to m. So, small b is equal to 1, and you can just replace this small b by 1, okay. And by definition, because this the definition of the system is that the mass of the system is fixed. So, this dm by dt of system will go to 0, and because of that we will have this expression, okay. Now, use the Gauss divergence theorem as earlier, okay, you will have this del dot rho u dV, okay, and then collect all the terms and assume that the system is stationary, okay. So, then you can take this entire thing inside the integral, and finally, what you get differential form, okay. So, between this and this, the consideration is that so this is conservation for the entire volume, and if we say that this conservation is allowed at every single elemental volume that we are taking, every single dV that we are taking, then we will get this differential form, okay. So, in the finite volume, we prefer to use this integral form, okay, and in the finite difference we go with the differential form. Although I mean this is called the conservative form, okay, and this is the differential form. So, although it is called the conservative form, okay, it does not mean that what we are doing in finite difference is not conservative. It is only the fact that in finite volume, when you do it, when you solve these equations, okay. So, our grid is basically made of different cells, right, as we have been discussing, okay. So, these are different cells, So, when we use this conservative form, okay, so this conservation law is basically applied to every single cell. So, in every single cell your conservation is applied. Okay. On the other hand, if we are using this infinite difference, the conservation is ensured through the boundary, right. So, through the entire volume, I mean the conservation of mass, momentum and energy will be basically ensured. It will not be ensured in every single elements that we have or the cells that we have. So, that is the difference between finite volume and finite difference, and both methods are popular and both methods can give you the desired results that you want. Okay. It has nothing to do with that if you are using conservative form, then you will get a better result than the finite difference. Although, when you are having shocks, then in those cases some people prefer to use this the integral form, okay, or the finite volume approach. Okay. So, now this is your differential form. Okay. Now, the same thing I will be using in the tensor notation, okay, and I will be following the tensor notation for most of this course. So, if you are not familiar with the tensor algebra, I would recommend that please go back and learn the tensor algebra, because this will really help you not only in this course, but I mean many courses in your engineering that you are pursuing. Okay. So, this is what we derived, del rho by dt plus del dot rho u is equal to 0. Okay. Remember, this is a vector, right. So, if you expand it, this will be d rho by dt plus del rho u by del x. If I am doing for 3D, del rho v by del y, okay, and del rho w by del x. Okay. Remember, there is a del operator, okay, which is dotted with the u operator. Rho is a scalar here. Okay. There is a reason we are talking rho inside the bracket, because we are not made any assumption whether the flow is incompressible or compressible, okay, till now. Okay. Now, this entire thing can be written in the tensor form in a very short way, which is d rho by dt plus del by del x I or del x j, whatever you want, rho u j is equal to 0. So, here j is the repeated index, okay, and it is a dummy index. So, if you use I or j or k, it does not matter, okay, LMN, whatever you want to use. Okay, it says that it is a repeated index. So, it will be repeating for like basically all the j values. So, if it is a one dimensional flow, then it will be just del rho by del t plus del rho u by del x. Okay. If it is 2D, then this is del rho by dt plus del rho u by del x plus del rho v by del y. And if it is 3D, then we have already, there was error here. Okay. So, this will be del by del y, w by del z, right. So, this is a repeated index, or it is also a dummy index, and this actually follows the Einsteinian convention or Einstein notation. So, earlier when tensor algebra used, so you had to write this del rho by del t plus sigma, okay, j equal to 1 to 3 del by del x j rho u j equal to 0, right, and then you do for j equal to 1 to 2, 1 and 2 and 3, right. But Einstein basically said that there is no need to basically use this sigma j equal to 1 to 3, because by default if there are indices which are repeating, that means the summation, you have to do the summation, right. And there is a story behind it that I think the Einstein's printer had some problem in printing all these things. So, he basically got rid of this, but now what is popular is basically Einstein notation only. Okay. Now, we have done this. Okay. So, now you can write this expression into many different form. Okay. So, what you can do, you can write it d rho by dt plus u j del rho by del x j plus rho del u j by del x j, j by del x j equal to 0. Okay. Now, what is this quantity? Okay. So, you can write it, if you are compared in vector notation, del rho by del t plus u dot del rho. okay, and plus rho uj by del xj. Okay. I am sure you are comfortable or you have seen this this kind of expression. It can be done for any derivative. So, del phi by del t, phi can be derivative plus u dot del phi. So, this is your time rate of change and this is the convection of that particle, right. So, this can go back to the discussion that we had regarding the system and the control volume. So, if you are in the control volume, you will have these two parts, okay. The flux or the advection is happening separately due to some motion, some velocity, and you have the time rate of change. But if you are into the system, this entire thing will come into one part, which is basically d phi by dt, right. So, this is basically the Lagrangian representation, and this is the earlier representation where you are not tracking the particle, but you are fixing a window and you are seeing how the particles, what is happening inside that window, right. So, you will have this fluxes going in and coming out, which will be given by this, and that is the advection, right. So, this entire thing can be written as d rho by dt plus rho del uj by del xj is equal to 0. Okay. Now, d rho by dt, if you go to the incompressible flow, so by the definition, the change of density following a streamline or the basically the total change of density is 0, basically that will become d rho by dt will be 0 for incompressible, right. That means, you will have rho duj by del xj is equal to 0 and rho cannot be 0, okay. Then you will have the expression del uj by del xj equal to 0, okay. So, that is your incompressible case, okay. So, for the incompressible case, del uj by del xj is equal to 0, which in the vector notation can be written as del dot u equal to 0, okay. So, this is the law or this is the actually expression that you use for the incompressible flow. Okay, where we say that the divergence, what is this? This is divergence of velocity is 0. Remember, when you go to the from compressible to incompressible, you lose the d by dt term, okay. So, there is no d by dt term present in the incompressible flow. So, it is not a dynamical equation, okay. It is basically it is a condition that has to be fulfilled by the flow, right, in the case of incompressible flow. In the case of compressible flow, you have this d by dt term, right. So, that is basically giving you the dynamics of the change of the density, right. So, because of that you have to do something special, because in the incompressible flow you will have let us say, even if you consider this density to be constant, you have u, v, w and p, right. But the equations that you have is basically the continuity or the mass conservation, okay, and then you have 3 momentum. Okay, so 3 momentum equation we are going to derive. There is no energy conservation for the incompressible flow. So, 3 momentum will give you the 3 values, okay. But the continuity is basically it is just a condition, it is not a dynamical equation, right. So, it is just del dot u equal to 0, right. So, you cannot basically solve all using del by del t, right. So, you need to do something special for the incompressible flow, because you have 4 unknowns and only 3 equations, okay, and then 1 condition, right. So, how to convert this condition del dot u equal to 0 to a dynamical equation, right, to determine let us say pressure, right. So, that is a challenge, and it is done by constructing another equation called pressure Poisson equation. So, we will discuss when we go to the compressible flow, but for now we have basically derived the law of mass conservation for the compressible and the incompressible flow. In the next class, we will derive the momentum conservation. Thank you.